Now we'll discuss inverse relations and inverse functions. So first of all, let's just remind ourselves what a relation is. So any set of ordered pairs we can consider a relation, whether it's a function or not. And an inverse relation is a result of interchanging the first and second coordinates of each ordered pair. So when we switch the first and second coordinates of each ordered pair, that produces the inverse relation. So as an example, if we have the relation, which is the set of ordered pairs 1, 2, -2, 3, -4, -5, and we just switch all the x and y values, then the inverse relation is the set of the ordered pairs 2, 1. Switching, we get 3, -2, and switching, we get -5, -4. So when you see this word inverse, I want you guys to think switch x and y. In one form or another, to find the inverse, you're swapping the x and y, you're interchanging the x and y, you're switching x and y. All right, so in the next box, it says finding an equation of an inverse relation. And again, it says interchanging the x and y variables produces an equation of the inverse relation. So again, we're switching x and y. So as an example, find an equation for the inverse of the relation y equals x cubed minus 4x. The inverse relation, if you switch your y and make it an x, you switch x cubed, make it a y cubed, switch x there to make that a -4y. You have x equals y cubed minus 4y. So you're switching the x and y. All right, so let's look at this in a little more detail. So for number 1, it says graph y equals x squared plus 1 by plotting the given points. So we're prompted with a little table over here. Then we want to graph the inverse relation on the same axes, and then we'll kind of compare them and see what's going on. So let's start with our first, our first function, our original, y equals x squared plus 1. And I'm just going to pull this up in my graphing calculator. This will be an upward-facing parabola. I can see the vertex is at 0, 1. So if I use the trace key for x equals 0, y equals 1. So we have the ordered pair 0, 1. Actually, sorry, let me change colors here. Okay, so we've got 0, 1. I can see that my parabola goes through that as the vertex. And then using the trace function for the other prompted x values, if x is -2, we get a y value of 5. If x is -1, we get a y value of 2. And skipping down, if x is +1, we get a y value of 2. If x is 2, we get a y value of 5. And that's just plugging the x values into the function. So for example, for +2, y equals 2 squared plus 1, 4 plus 1, which gives us the 5, right? So plotting all of these points, we have -2, 5, -1, 2. I already plotted 0, 1, the vertex. Then we have 1, 2, and then we have 2, 5. And I'm going to connect all of these. So this is my upward-facing parabola. So this is my original function, y equals x squared plus 1. Okay. Now let's just pause for a second. If I were to apply the vertical line test on that original function, so the vertical line test, and I have a little sketch of the original down here at the bottom, it's going to pass the vertical line test, right? Any individual vertical line that we draw is going to intersect at most one time, right? So any vertical line intersects once. So applying the vertical line test to the original confirms that the original is a function. My original equation is a function. Okay, so I just want to mention that. All right, so we're looking at a function. It's a parabola. Super. Now let's take a look at its inverse relation. And if we wanted to write an equation for this, we could take y equals x squared plus 1 and just switch the x and y, which gives us x equals y squared plus 1. So notice over here for the inverse relation, for the inverse relation, instead of just x, now I have x equals y squared plus 1, and then I have y listed over here. So on the first table on the left, the given x values were -2, -1, 0, 1, and 2. Now those are my y values here because I switched x and y. So now my y values become -2, -1, 0, 1, and 2. And I want to write the corresponding x values. And the corresponding x values will be what the y's were from my original equation. So 5, 2, 1, 2, and 5. Just copying from the y column in the original into the x column for the inverse. I'm switching the x and y coordinates. So let's go ahead and plot these points and see what they look like. So first I have 5, -2. I have 2, -1, 1, 0, and then 2, 1. And then I have 5, 2. All right, and let me go ahead and connect these. Okay, so that's our inverse relation, x equals y squared plus 1. All right, so a couple of things I want you guys to note. Any inverse relation will be symmetric about the line y equals x. And that's this dashed line here. So any relation and its corresponding inverse will be symmetric about the line y equals x. So that's a really important fact that I want you guys to remember. Y equals x, if you were going to plot that, which obviously it's already plotted, but y equals x, it goes through 0, 0, where the x and y equal each other. It goes through 1, 1, where the x and y equal each other. 2, 2, where the x and y equal each other. So whenever x equals y, it produces this line with a slope of 1 that passes through the origin. So that's y equals x. A relation and its inverse relation are always symmetric about the line y equals x. Okay. Now, the next question in this paragraph, it says, is the inverse relation a function? So we can determine if something is a function or not using the vertical line test, right? So now that that inverse is drawn in purple, and I have a follow-up little sketch down here so I don't mess up my original graph too much. If we apply the vertical line test, to this inverse function, it fails, right? So if we apply the vertical line test on the inverse, one vertical line touches the graph twice, right? One vertical line hits the graph here and here, hits twice. So that means that the inverse is not a function. Okay, so this inverse relation is not a function. So we can determine that just by applying the vertical line test to the inverse now that it's drawn out. Is there another way that we could determine whether the inverse relation will be a function? And the answer is yes, and it's something called the horizontal line test. So the HLT, the horizontal line test. So what the horizontal line test does is it's kind of a predictor. It's a little bit of a crystal ball. So before we even graph our inverse relation, what we can do is apply the horizontal line test to the original function. So if I apply the horizontal line test to the original, it's just like the vertical line test, only I'm drawing a horizontal line. And you can see that one horizontal line hits my original graph twice. So the horizontal line test on the original hits that graph twice. That tells me that when I reflect this across y equals x, when I reflect this into its inverse relation, that tells me that the inverse relation is not a function. Okay, so you apply the horizontal line test to the original function. It's a horizontal line, and if it hits the original graph twice or more, then you know that the inverse relation will not be a function. We could also graph the inverse, apply the vertical line test. That's double confirmation that the inverse is not a function, but we could have known that before we even graphed the inverse by looking at the original. So there's the vertical line test and then the horizontal line test. The horizontal line test you apply to the original to decide whether the inverse will be a function or not. Okay. And you could even apply the horizontal line test to the inverse. So the horizontal line test on the inverse over here would only hit my graph once, right? So the inverse of the inverse is the original. So in this case, that confirms that the original, which is the inverse of the inverse, the original is a function. Okay, but we really don't ever do this. That would be kind of weird, but we could. So for the original function, you can apply the vertical line test to tell if the original is a function. And then you can apply the horizontal line test to the original to decide whether the inverse relation is a function or not. If it only hits once with a horizontal line, then you can expect the inverse to be a function. If the horizontal line hits your original graph twice or more, then you know that your inverse will not be a function.